Poisson's ratio is such an important material property because it gives us key information about how different materials deform under loading. Let's get right into it. We can start with a quick example, the rubber band. If you take a rubber band and stretch it along its length will obviously increase, but it is also quite intuitive that at the same time the band will get thinner. Poisson's ratio can tell us how much thinner the band is going to get. What about for a generic lump of material? Take this little orange cuboid. If we apply a compressive force to it, it will expand in the directions which are perpendicular to the direction in which we are applying the load. We call the direction along which the load is applied the longitudinal direction, and we call the perpendicular directions the lateral directions. If we reverse the direction of the force to apply a tensile load, the cuboid will obviously extend in the longitudinal direction, and it will contract in the lateral directions. The key concept here is that when you apply a load to a material in one direction, the material will also deform in the lateral directions. Poisson's ratio is the parameter that tells us how much the material will deform in the lateral directions. To define Poisson's ratio more precisely, let's take a closer look at the case where a tensile force is applied. First, let's give names to the various parameters involved. Lx, Ly, and Lz are the original dimensions of our cuboid along the x, y, and z axes. Delta Lx, delta Ly, and delta Lz are the changes in these dimensions after the load has been applied. They are shown as being divided by 2 because the change in dimension occurs on both sides of the object. Next, we can write out the strains in all 3 directions. As a quick reminder, strain is a measure of deformation and is defined as the change in length divided by the original length. It is denoted using the Greek letter epsilon and is usually expressed as a percentage. When we apply our longitudinal load, it turns out that the resulting strains in the lateral directions are equal. And here's the interesting part. They are proportional to the strain in the longitudinal direction. The ratio between the longitudinal strain and the lateral strain is actually a material constant. You might have guessed it by now, but we denote this material constant with the Greek letter nu, and we call it Poisson's ratio. By the way, Poisson's ratio is named after this guy, Simeon Denis Poisson, the famous French mathematician who formally defined the ratio in a note published in 1827. You might be wondering why a minus sign slipped into the equation. Remember that by convention, tensile strains are positive and compressive strains are negative. The minus sign is just there so that for the typical case where the lateral strains are opposite in sign to the longitudinal strains, we get a positive Poisson's ratio. Now is probably a good time to mention that this equation and the concepts described in this video only apply for isotropic materials, which are materials which have the same properties in all directions. We are also assuming that the materials are deforming within the elastic region. Things get a bit more complicated when plastic deformation is involved. Anyway, to summarize, Poisson's ratio is a dimensionless material property, which tells us how much a given material will contract in the lateral directions when we pull on it in a longitudinal direction. Now that we know what Poisson's ratio is, we can look at some typical values for different materials. Without getting too deep into the math behind it, it's useful to know that the theoretical range of possible values for Poisson's ratio goes from -1 to 0.5. In practice, most real materials have a Poisson's ratio of somewhere between 0 and 0.5. Most metals have a Poisson's ratio of around 0.3. Here are some typical values for a few selected materials.